If you open a standard digital document right now, what you're actually looking at is, well, it's kind of a lie.
Yeah, a very convincing line.
Exactly. I mean, the bold text, the centered headers, the paragraph breaks, all of it. It's just this visual hallucination. And it's covering up a massive, completely hidden structural reality.
Right, and that hidden reality is entirely rigid. I mean, as readers, we forgive a lot, right? Like a missing comma or a weird formatting quirk.
Oh, sure. Your brain just fills in the gaps.
Exactly. But software demands this absolute, uncompromising hierarchy just to render a single bold word on your screen.
Which brings us to our mission for this deep dive. Today, we are looking at what happens when a machine strips away that visual illusion and how the developers building these machines have to literally rewire their own cognitive models just to make sense of the text.
It's fascinating because we're really examining how human intention gets mapped into machine structure and, the profound friction that happens when the language of the machine completely conflicts with human intuition.
Yeah. Right. And our source material today gives us a perfect window into this. We are diving into a highly detailed set of developer notes from April 29, 2026.
Yeah, specifically, we're looking at part 122 of a blog series.
Part 122.
I know, right? It's a series on Haskell programming by a developer named Ang. And the fact that it's part 122 just shows you the staggering amount of architectural history behind this project.
It's massive. Okay, so let's unpack this. We're exploring how software parses a document, sure. But the real core of this is understanding how a developer's choice of just like one or two seemingly tiny symbols completely changes the way human beings process logic.
Yeah, that's the real story here.
If we think of a standard text document as a physical body, it's like Aang is taking an X-ray to examine the skeletal system underneath.
And that hidden skeleton dictates everything about the software lifecycle. I mean, it determines how fast the application runs, how prone it is to edge case errors, and most importantly, how clearly the developer can actually reason about the data.
Right, which affects all of us. Whether you write Haskell code for a living or you literally just use a word processor to type a grocery list, the mechanics we're discussing govern the digital text you consume every day.
Yeah, exactly. And the center of all this tension is the developer trying to construct that skeleton without the structural logic just, well, collapsing in on itself.
So to understand why a tiny syntax symbol changes how a developer thinks, we first have to examine the massive structure Aang is attempting to build, right?
The project is an application called X2 eBook. And the primary challenge Aang is writing about in this specific journal entry is mapping.
Okay, let's break that down. Aang has constructed a custom abstract syntax tree, an AST, right?
Yep, an AST. And Aang needs to translate that custom tree into Pandoc's internal AST.
Pandoc, for those who might not know, is basically the universal translator for document formats across the whole software world.
Exactly. And to perform those translations, Pandoc relies on its own highly specific abstract syntax tree, which is, the literal data structure representing the text.
Right.
Aang provides this brilliant command line example to really demonstrate what this looks like in practice. So imagine you take the phrase, hello world, but you emphasize the word hello by wrapping it in asterisks.
Okay, simple enough.
Right. And then you pipe that into Pandoc's native format. The command looks like echo quote, hello asterisk space world quote, and you pipe that to Pandoc-temp native.
And the raw output of that command, it completely exposes the skeleton. It spits out this huge string. It's like bracket para, open bracket env, open bracket strike quote, hello end quote, comma space, comma strike quote, world end quote, close brackets.
Yeah, it's intense.
It is. It translates basic formatting into this series of nested mathematical sets. When I was reading the source, I pictured this mechanically, like Russian nesting dolls.
Oh, that's a perfect way to look at it.
Right. You open the largest doll, which represents the entire paragraph or the para tag, and inside that structure, you find a distinct doll just for the emphasis.
Yep, the env tag.
And that one holds an even smaller doll containing just the string hello. But then, right next to that emphasis doll, the machine requires a completely distinct doll simply to represent the empty space between the words.
Yeah, the literal space character has its own structure.
It's crazy. And then finally, a concluding doll for the string world.
And that recursive nature, those nesting dolls that defines how an abstract syntax tree operates mathematically. You establish a root trunk, which is the entire document, and then you branch out into two distinct categories.
Blocks and inlines, right?
Exactly. Blocks are your foundational structural elements. They're the really large nesting dolls. The paragraphs, the headers, block quotes, they establish the whole flow of the page.
And then the inlines are the microelements inside them, the raw text, the italics, the hyperlinks.
Right. So Eng's core task here is taking the custom nesting dolls generated by the XS2 book application and translating them seamlessly into Pandoc's highly specific dimensions.
But translating those nesting dolls across systems exposes a massive flaw in how text is handled in strict programming environments, doesn't it?
It really does, because every time you cross a structural boundary, the compiler demands an explicit translation.
Right. The notes show Ang processing a list of tokens, metadata, headers, paragraphs, and mapping them using a core function called foldMap. And that's paired with a custom-to-Pandoc function to try and generate this continuous mapped document.
Yeah, so foldMap is this very fundamental concept in functional programming. It basically relies on traversing a data structure and combining all the results. You give it a list of items and a strict set of mapping rules, and it just processes them sequentially.
It essentially operates like a snowplow moving down a street.
A snowplow.
Yeah, think about it. It drives through your list of tokens, applies the translation rules to each one, and continually accumulates the results into one giant pile, or, in this case, one continuous structural document.
Okay. Yeah, I like that. But pushing that snowplow introduces immense administrative friction for the developer.
It does. The code gets cluttered with boilerplate so fast. Ang notes this deep frustration with what is described in the source as alphabet soup.
The alphabet soup.
Yes, it's because of the constant need to inject this command called toStrict.
Right. And to understand why that's happening, you have to look at how a strict functional language like Haskell handles memory. The memory representation of data matters deeply.
How so?
Well, a string of text might be represented conceptually as a string type, which, under the hood, is literally a linked list of individual characters.
Huh.
Very slow, very memory intensive.
Okay.
Alternatively, it might be represented as text, with a capital T.
Hi.
That is a much more efficient packed array in memory. But because Haskell guarantees memory safety, these two types, string and text, they do not interact automatically, ever.
Wow. So Ang is forced to manually write strict to convert one text type into the other over and over again?
Exactly. Before the actual mapping logic can even execute, you have to do this conversion, otherwise the compiler throws a massive error.
That sounds exhausting. It's like, imagine I'm writing a highly technical research paper, right? And I have to pause every third sentence to manually update a glossary before I am legally allowed to finish my thought. My cognitive flow would be completely shattered. The administrative overhead of managing the glossary completely eclipses the complex logic I'm actually trying to communicate.
That is exactly the friction Ang was feeling. But Ang resolves this by globally enabling a language extension called OverloadedStrings.
OverloadedStrings, what does that actually do?
It shifts the entire administrative burden away from the developer and puts it directly onto the compiler. It basically instructs the compiler to analyze the surrounding context of the code and automatically infer the required text representation in memory.
Oh, that's huge.
Yeah, it stops forcing the developer to explicitly state the conversion at every single boundary.
So it is literally the equivalent of hiring a real-time interpreter who handles all the syntax conversions silently in the background, allowing you to focus entirely on the architecture of your argument.
Precisely. And the broader takeaway here, really, for anyone listening, regardless of your industry, is that friction in your medium restricts the depth of your thought.
That is such an important point.
When Ang eliminates that boilerplate administrative work, a string conversion, the mental energy immediately shifts back to the architectural logic of the project itself.
But removing that mechanical friction actually exposed a bigger problem, didn't it? It exposed the underlying structural philosophy.
It did. Fixing the string conversions was totally necessary, but it revealed to Ang that the actual direction of the logic still felt fundamentally backward.
Okay, here's where it gets really interesting. We are moving from the mechanics of text conversion into the literal direction of logic processing.
Right. To demonstrate this, Ang analyzes a code snippet dealing with document metadata, specifically configuring the title and the author of the document. And this snippet relies heavily on the $sign operator.
The $sign operator, which in Haskell dictates execution order. Its defining characteristic is that it forces the compiler to evaluate expressions from right to left.
Right to left?
Yeah. So Ang's code sequence looks like this. Set title space $, space, set meta with the author data, space $, space, empty.
And tracing that evaluation order reveals the massive cognitive load it requires from a human reader.
Hmm.
Because it evaluates right to left, the compiler literally bypasses the beginning of the line and starts at the absolute end.
It skips right over the title.
Completely. It goes straight to the far right. It finds M empty, which initializes a blank state, an empty canvas for the metadata.
Okay.
Then, moving left, it encounters set meta, which takes that blank canvas and applies the author data. Then, moving left again, it finally executes set title, taking the canvas that now holds an author and appending the title to it.
Eng conceptualizes this right-to-left process as wrapping an onion, which I just love. To comprehend what the code is doing, human intuition has to jump to the very center of the onion, the M empty blank state on the far right, and then mentally peel outward layer by layer, moving leftwards to deduce how the final result is assembled. Eng identifies that this creates a deeply indented staircase issue.
Yeah, that staircase issue is a nightmare for readability.
Mm-hmm.
Every time you add a new functional layer to the onion, the code physically pushes further to the right on the screen.
It just keeps indenting.
Exactly. It creates this descending visual staircase that becomes incredibly difficult to scan, process, and maintain as the project scales up.
But during a self-review phase, while literally drafting the blog post we're reading today, Eng isolates this cognitive friction. And Eng replaces the $sign with an alternative symbol, the ampersand.
Yes, the ampersand symbol. It serves as the reverse application operator, which you import from the data.function module.
And that single ampersand flips the entire architectural model of the sequence, doesn't it?
It completely inverts it. The code can now be read smoothly from left to right. It functions very similarly to the pipe operator found in the Elixir programming language.
So instead of wrapping an onion, you initiate the sequence with M empty on the far left. You pipe that blank state into set meta, and then you pipe that result into set title.
Blank canvas, add author, add title. Boom.
The onion is transformed into an assembly line.
That's a great way to put it.
But this brings up a huge question for me, and I think for you listening as well. If reading left to right intuitively solves the staircase issue, and it perfectly aligns with human cognitive flow, why would a programming language be designed backward in the first place?
Well, that question really interrogates the core identity of Haskell itself. The language isn't designed backward arbitrarily, I promise. It is constructed to rigorously mirror pure mathematics.
Okay, unpack that for me.
Its foundation is deeply rooted in lambda calculus. In standard mathematical notation, function definition follows a strict, unyielding order. When you write f of x, the function f universally precedes the data, x.
Right, the action has to be defined before the entity being acted upon.
Exactly. So when mathematicians compose multiple functions together, for example, applying function g to a set of data, and subsequently applying function f to that output, the notation is written as f.g.
Ah, right.
And you read that sequence right to left. Haskell's $sign operator exists to preserve this mathematical purity. It treats the entire codebase as a strict equation where functions are composed from the outside in.
But by forcing a left-to-right flow with the ampersand, you disrupt that mathematical purity. By prioritizing the data flow, you break the structural precedence of the functions. Which means, according to Eng's notes, you lose the elegance of one of functional programming's most powerful tools.
Currying.
Yes, partial application or currying.
The mechanism of currying is so essential to understanding this trade-off. Currying is a structural concept where a function that requires multiple arguments can be supplied with fewer arguments than it actually demands.
And it doesn't just crash.
No. Rather than failing or throwing an error, it returns a new intermediate function that is suspended in state, just waiting for the remaining data.
Okay, wait, let me try to ground that mechanism for everyone. Say I have a complex function designed to multiply 3 distinct integers, but I only feed it say, 2 and 5.
Go.
Currying means the language generates a temporary function that acts as a multiply by 10 machine. That machine sits in the execution pipeline, simply waiting for the final integer to arrive. Is that right?
That is perfectly accurate. And for that suspended waiting mechanism to function seamlessly within a chain of operations, the primary piece of data, the final integer in your example, must be the absolute last argument provided.
It has to sit at the very end of the expression.
Exactly. A right-to-left evaluation order perfectly feeds that final piece of data directly into the waiting function at the exact moment it is needed.
Oh, wow.
Yeah, if you invert the flow to left to right, you are feeding the primary data in first. This completely shatters the mathematical notation of providing the function prior to the data, and you lose the ability to easily chain those partially applied waiting functions together.
So we are really looking at a massive philosophical divide in software architecture here.
We are. On one side, we have pure mathematical theory, where functions compose inside out and data is fed backwards into waiting parameters.
And on the other side, we have the sequential flow of data moving down a left-to-right assembly line.
Right. And Ang synthesizes this debate by evaluating the specific structural requirements of the Access to ebook project itself. You see, Ang brings a historical background in Python and Elixir to this project.
Both of which are languages that strongly favor data-first, left-to-right execution pipelines.
Exactly. That mental model feels inherently natural to Ang when the core task is constructing an abstract syntax tree.
Because constructing those recursive Russian nesting dolls from scratch relies on what developers refer to as the builder pattern. You instantiate a blank state and incrementally attach properties to it.
Yeah.
The left-to-right flow objectively mirrors the physical act of construction. Base, frame, walls, roof. You do not build a physical structure from the inside out like a mathematical equation.
No, you definitely don't.
So Ang's decision to implement the ampersand resolves the cognitive friction because it perfectly aligns the syntax of the language with the physical reality of the task being performed.
Which is brilliant. And there is a profound meta lesson embedded in the source notes regarding how this architectural alignment was actually discovered in the first place.
Yeah, I wanted to bring this up.
Ang explicitly documents that the entire insight concerning the ampersand operator only materialized because time was taken to actively write a blog post analyzing the code.
Writing down the problem solved the problem. The act of articulation functions as the ultimate debugging tool.
It really does. When a developer is buried in compiler memory errors and deeply nested functional parameters, tunnel vision is totally inevitable.
Right. Forcing yourself to explain your structural logic to an external audience demands that you zoom out and translate pure machine logic back into conceptual human language.
Documenting the problem exposed Ang to structural alternatives that were completely invisible while fighting the alphabet soup down in the trenches. Self-review through the medium of writing forces cognitive distance. It forces the brain to evaluate the architecture rather than just staring at the immediate syntax error.
That is so true, and it goes way beyond code. The structural flow and syntax you choose directly dictate the clarity of your broader thinking.
Oh, absolutely.
I mean, if you manage an operational team, right, and you rely on deeply nested, sprawling email chains to communicate project updates, you are essentially building an organizational onion.
Ah, an organizational onion. I like that.
You create the exact same staircase issue that Ang faced, making long-term maintenance and visibility virtually impossible for your team.
But transitioning that team to a clean left-to-right project management board transforms the operational onion into a functional assembly line. The medium shapes the message, and the syntax dictates the workflow.
We began this analysis by examining the hidden skeleton of a digital document. We explored how an abstract syntax tree enforces a rigid hierarchy to map human intention into machine reality.
And by simply swapping a mathematical dollar sign for a sequential ampersand, Ang demonstrated how a developer can shift an entire cognitive model from inside-out mathematical composition to a streamlined left-to-right data flow.
It really serves as a rigorous masterclass in aligning the specific syntax of the tool with the precise mental model required for the execution of the job.
Absolutely.
So if the language and the structural tools we use literally shape the direction of our underlying logic, you have to ask yourself, when you sit down to solve a complex problem in your own work tomorrow, whether that involves writing software architecture, drafting a strategic proposal, or simply organizing a data set, are you unknowingly letting the default syntax of your tools dictate your solution?
It's a great question.
Are you building a sequential assembly line when you should be writing a foundational equation? Or are you wrapping a convoluted onion when all you really need is a straight left-to-right path forward? Take a close look at your own X-ray. You might be surprised by the skeleton you find.